It actually would require two surfaces, right, to enclose that? But your normals need to point away from the solid. So does it make sense to you that I could write this? Just see if this makes sense. That the triple integral over E of the div of f, by the way, there's a vector field sitting here. F is here, PQR. I need a vector field or I can't talk about flux, right? Okay, so there's some vector field sitting here in the background the whole time. Do you agree that this should be equal to the surface integral over S of f ds, where S encloses E, right? So don't confuse S with S1 and S2. S is the surface that encloses the bread of the donut. Can we go with that? Good, I'm glad you mentioned that because I think it makes sense. So S is actually made up of two surfaces. One is S2, right? And the other one is S1. Now, is S2 oriented properly in terms of how it encloses E? Are the normals pointed away from the bread? Yes? So I could say that this is equal to the surface integral over S2 of f dot ds plus now the other surface, which is S1, right? Do the normals of S1 point away from the bread? No. So I need them to if I'm going to orient it properly, right? So instead of looking at S1 normals pointed towards the bread, I'm going to reverse them. So when I reverse the direction, it changes the sign of the integral from plus to negative. And now it's S1f dot ds. Does that make sense to you? Okay. If we have a solid that is between two surfaces, then that formula should hold, right? I'm going to erase all this, and I'm going to start the problem. I just need this in a minute, all right? I want you to consider in three-dimensional space an electric charge, which I will call Q, capital Q, at the origin. Okay, so imagine that we just have something that has a charge to it. Positive, negative charge, it has a charge. And I'm going to say, here it is, and I'm going to call that the origin. All right? So I've got this picture. I've got something sitting here, and it has an electrical charge on it. All right? When you take a physics class, they will tell you, due to, how do you say this? Coulomb's law. Will say that the electric force which we will call f of x, all right? The electric force is a field. So imagine that this is creating a field, all right? The electric force f of x. Now, x is a vector, so you plug a vector in to this field and you get an answer, and that's your force. The force of Q on another charge, lowercase q, at the point x, y, z, or if you'd like, you can look at that as a vector, x, y, z, is equal to E Q, capital Q, over magnitude of x cubed times x. Anyone? Oh, I forgot the equal sign in here. I was hoping that someone had seen this before. Yes? Some version of it, or close? Look close?
Yeah.
Okay. Here, do they use epsilon? What do they usually tell you for that? Epsilon, okay. Epsilon is a constant, and that constant depends on the units that you want to measure in. Okay? What I'm trying to do today with this example is show you a physics problem that there's a formula for something here in a second that I'm going to derive the formula. All right? So this is the electric force. But in physics, they're not interested in the electric force. They're interested in the force per unit charge. So what they do is they come in, they take this vector field. This is a vector field, isn't it? There's a vector in here. Okay? These are all numbers, aren't they? Number, Q is a charge. It's going to be a number. Capital Q is a charge. That's a number. This is the magnitude of a vector. That's a number. So this is all a number times a vector. So that's a vector. It's a vector field. If we define a new vector field, capital E of x, to be equal to that field divided by Q, then what would happen if I take this field and divide it by Q? Little q. Little q's cancel, right? And I just get E epsilon Q over x, magnitude of x, times the vector x. Okay? And this is your force per unit charge. Or, yeah, force per unit charge. I'll put it here. Force per unit charge. And this is something that will always hold for any charge that you put at the origin, and then you place another charge out here relative to it. This has a position, right? The position of this is x, y, z. Then the force per unit charge is some measurement of what's happening between these two, right? Got it? How these two charges are interacting with each other. All right, what do I want to do now? I want to get to the problem. This is the big thing we're going to work with right here. I want us to show that the flux of E with respect to S, okay, so this surface flux is equal to 4 pi epsilon times Q. Does that all look familiar? I don't know. Maybe you've seen that. Maybe. That this is equal to that for any S which encloses the origin. That's it. That's what we want to show. So if I put a charge here, if I put charge Q at the center here, have another charge here, then the force per unit charge along a surface, right? You have this surface. Imagine any three-dimensional surface, right? That encloses the origin. So it encloses our charge, right? That will always be this right here, which means it's always a constant, but it depends on the charge that you started with. Okay, so you change this charge, this is going to get bigger or smaller depending on Q. We want to show that that holds for any surface that encloses the origin. Now, we ran into a problem like this a while back. I showed you this example where we were trying to show something for any circle that, or any curve that enclosed the origin. Do you all remember that? And we were able to do it. We were kind of sneaky about it, but we did it. I'm going to do something similar here. All right, so the first thing I'm going to do, here's my picture. I want us to call this surface right here, just to make it easy to go back and look at what we drew a second ago. Let's call this right here S2. All right? So this surface that encloses our origin point, this is S2. I would like for us to consider S1. So this is my solution. Consider the surface S1, which is going to be a sphere of radius A, which is inside S2. So do you agree that if somebody gives me a surface that encloses the origin but does not actually touch the origin, that I can always find a small enough sphere to fit inside of S2? You agree with that? You have to agree with that. Yeah. You're okay with it? Okay. So this inside of here, it might be really small, but I should be able to control I pick a radius which is going to make it small enough to fit inside. So here I go. Here's my sphere sitting inside. That's S1. You still with me? Yeah? All right. This looks a lot like the donut, right? That we did a second ago? What can you tell me in terms of what we did before? If E is the solid between them, be very careful there, solid between them. Please put it away. If the E is the solid between them, which is the bread part, right? Then what can we say? I wrote down a thing here a second ago. Yes, it's the triple integral over E of the div of F, right? dV. Our field here that I want to be working with is E, okay? Don't confuse these two E's. F was the force field, but I said let's define E to be the the force per unit charge. So do you agree that our new field out here is the field E, not to be confused with the solid inside, which is just E without a vector? Should I change the name of the solid, or are y'all okay? Okay. All right, so this should be equal to what? The surface integral over S2 of E dot ds. It's still with respect to surface area, so ds. Then what? Minus surface integral over S1 of E ds. We still good? Now, if you remember how I snuck in and did the other problem, I was able to show one of these with something real quickly and easily. I'm going to do something similar here. I'm actually going to work on the left side of this right now, which means I want to find the div of E. All right? What's going to happen is that this is actually going to become 0. And because it's 0, that means that these two, when I move this one to the other side, must be the same. And if these two are the same, that means to find the this flux over S2 is equivalent to finding this flux over S1. And I can do that because I have a nice, good definition of what S1 is, right? But I still have to show that the div of E is 0. So that's what we get to do now. So I'm going to say here now, but the div of E equals, well, what is E? Div of, it's a vector, isn't it? Tell me what E was. It was epsilon q over magnitude of x cubed times x, right? That was it. But what is x? What is this x vector? Maybe we never stated that from the beginning. The x vector is the vector that goes from the origin to little q, which is just the point x, y, z, which is the vector x, y, z. So I want you to convert this now to say this. E, or epsilon times q over what is the magnitude? What is the magnitude of x? Square root of x squared plus y squared plus z squared, all of this cubed, right, times x, y, z. Right. This is a constant. I multiply it through. So this becomes, I forgot to put my div in here. I haven't taken the div, have I? No. I'm taking the div of this. I'm taking the div of this. I'm going to do that as I work through here. So I need to do the div of, as a vector, it's x times this, right? So EQX over root x squared plus, it's about to be junk. Give me just a second. And then here, E epsilon q y over square root of x squared plus y squared plus z squared. And then epsilon q z over square root of x squared plus y squared plus z squared. I need the div of that. So maybe we can do what we did a second ago. We can just look at one of them and see the pattern in the derivative and just do the same for the rest. Okay, what is the partial with respect to x of epsilon qx over root x squared plus y squared plus z squared? All right, quotient rule. Derivative of the top with respect to x, epsilon q times the bottom. I'm going to go root junk, right? Root j. Minus the top, epsilon q x times the derivative of the bottom, which is 1 over root junk. Yeah, you're going faster. 1 over 2 root junk times the derivative of what's in there, 2x, and that's it for the top, right? All of this divided by root junk squared. So just junk. We still good? 2's cancel. See if. We did. Hold on. This is bad. This is bad. No, we didn't forget. I forgot. Yes. Yeah, do y'all see that? Look, when we distribute this cube, do y'all let me forget this? You did on purpose. Look, I'm going to rewrite this to the 3 halves. Is that all right? 3 halves. That's going to change some things here, isn't it? 3 halves. We got to start this over. I think the top, this is the same, but it's not root junk, it's junk to the 3 halves. This is the same. Yeah, I'll get to that. Let's do this part right here. Okay. We're right there? All right, well, derivative of this is 3/2 the junk to the power came down.